converted into B with a rate constant K1, and B is converted into A with a rate constant of K minus 1. And what we can do is actually we can break this more complex reaction down into two elementary reaction where we say A is converted into B, K1, and B is converted into A at a rate constant K minus 1. Now we can write for the change, the rate of change for the concentration of A, dA over dt equals nothing else but this reaction here plus the rate equation for this reaction here. And we know that we can express these things. So we can say, for example, dA over dt equals, so if we look at this part here, we can say minus K1 times A to the power of M, so that's the concentration of A, plus, now in this case A is produced, so plus K minus 1 times the concentration of B to the power of, let's call it N. Very often these M and N coefficients are 1, but they don't have to be. Now, this equation is generally valid, so we don't have to make any assumptions here. However, at a certain point, we can imagine that the forward reaction, this one here, equals the reverse reaction here. So what would happen in this case is that the forward reaction is exactly the same as the reverse reaction. As much as A is consumed, A is also produced. And in this case, there wouldn't be any change. So this particular case, we can write dA over dt, and that should be 0. And if this is 0, then we are talking about an equilibrium. So in the equilibrium, there is no change in the concentration of A. So how can we express the equilibrium? Well, we can just simply say 0 equals minus K1 times A to the power of M plus B to the power of N times K minus 1. I haven't written that very nicely, but it doesn't matter. So what we can do now is we can get this expression here to the other side, and we get K1 times A to the power of M equals K minus 1 times B to the power of N. And what we can do now is we can bring all the rate constants to one side and all the concentrations to the other side. So what we get is K1 over K minus 1 equals B to the power of N divided by A to the power of M. And that this actually is the expression for the equilibrium, which is true as long as dA over dt, and of course dB over dt,